Please welcome our second speaker of this evening, Mark Nottingham from Fastly. Hello Mark, welcome to Nottingham.
I think we need welcome back. Hi everybody, I'm Mark. Like I said, I work for Fastly. Sometimes I describe what I do as I try to do things to the internet. I'm going to be talking about something I'm actually really excited about, which is structured headers. Excuse me. You know, the HTTP community has been involved and fascinated with improving HTTP now for more than a decade. We worked on HTTP 2, put a lot of effort into that, a lot of time, a lot of developer resources. Now we're working on HTTP 3. That seems to be going pretty well, as you heard from Lucas. We're on track to shipping something sometime soon. And so we started to look around and say, okay, well, what else needs improving in HTTP? What else can we do to make this protocol, which we as a community have put huge amounts of effort into, and because it's deployed so widely, has a huge amount of implicit value to the internet, how do we keep it, working for as long as possible so we can extract as much of that value as possible? And one thing came to mind. HTTP headers are actually really horrible. Most of you are familiar with this kind of form of HTTP header. Okay, keys and values, little tokens, maybe you have some commas separating them. And, ones like this. The problem is that the parsers for these headers in browsers and servers are completely different. Each one is bespoke. And the way they handle things like white space and ordering and delimitation are completely different. And so they're special little, I won't say it. And you have this other property where, yes, we can serialize headers as separate things, or you can combine them with commas, and these are known to be semantically equivalent. And that's another major feature of HTTP headers, except when it's not. Because somebody had a great idea and put a comma in a field that wasn't, quote, delimited. So now you need another special little parser just for these things. And there's actually an exception in the HTTP specification just for setCookie, which is really annoying. So here's another thing that's annoying about HTTP headers. We specify them usually using this thing called A, B, and F. Who's familiar with A, B, and F? I'm sorry. It's this little language that you use to specify syntax. So here it's one or more cache directives separated by commas, and each cache directive is a token, then optionally equals a token or a quoted string. Fine. So, cache control max age 3600. That's invalid, right? Because look, there's a space there, and it doesn't allow any space, right? Well, implementations are unsure about that. The white dot means that they think it's invalid, the circle means that they don't. This is from a test suite that we wrote for how caches work. And that's because RFC 2616, in its great wisdom, said that linear white space is implicit. That anywhere you can insert some white space, yeah, go ahead, it's fine. But that rule is buried way up in one little part of the spec, and most implementers didn't bother to read it, they just looked at the examples. Because that's what developers do, right? Okay, what about this one? Surely, you put some random trash on the end, that's going to make it fail, right? Well, sometimes. So, that's not great. It's not great. Interoperability is why we're doing this, right? This isn't good. And so what this has led to is cutting edge in the community right now is to do this, like CSP does, where you specify step-by-step an algorithm for how to parse a header, which is enormously painful. Not only for the person running the spec, I really feel for them, but also the implementers. And so they have to go and implement this algorithm and make sure they get it right, and if they don't, then they're not interoperable for every single header. So, summarize. Writing a spec is difficult for a header because, ABNF is, it's good at what it does, but it's not really matched with modern practice. Writing and implementing these parsing algorithms one by one is really painful. And very, very often, when people write these specs, they forget error handling. What happens when there is white space and it shouldn't be, or what happens when there's an extra thing there, or whatever. And they don't specify the air conditions, and therefore, air handling differs from implementation to implementation. And those are the thorny little edges that cause interoperability problems on the internet, or indeed even security problems. So, we have ill-defined headers. They don't leverage any common syntax beyond the bare basics. They kind of look the same, but they're not. And usually, like I said, it's a one-off. Security performance both suffer because we're spread out doing all these things again and again. You talk to the browser implementers, and they'll often tell you each header has its own separate little parser that somebody wrote way back when, squirreled away in some part of the code, and they're all separate. And that's a nightmare. Yeah. So this is the structured header spec. We saw this problem. We thought we could probably do better. There's a long history here of different proposals, which I won't go into, but this is the current spec. I'm an editor, and so is Paul Henningkamp. It is currently in working group last call in the HTTP working group. We're almost done. Please don't raise any more issues. And what it does is it defines a bunch of item types, atomic item types. You've got integers and decimals, not floats, it's not floating point, it's fixed point, strings, tokens, booleans, and byte sequences. And these are all the ways that they appear in HTTP headers. And you notice that they're each distinct. You can examine the first character and say, okay, the first character is a number, so it's either an integer or a decimal. There's a parsing algorithm for that. The string starts with double quotes. Tokens is it's alphabetic, not alphanumeric. And it doesn't have quotes. Boolean starts with a question mark, and byte sequences start with a colon. And that way a parser can reliably identify what kind of data type it is encountering. All of these individual item types can be parameterized, so you can add information to them and say, okay, it's an integer, but it has a parameter of foo or whatever, and that's so you can extend it with further semantics down the road. And then we define a bunch of, actually just a couple of container types. We used to have a bunch, now it's just a few. We've got lists, fairly obvious, I hope. Inner lists, which is not quite as obvious. It's a list of lists, effectively, so you can have a little bit of nesting in your data structures. It's not recursive. A lot of the implementers felt that would add too much complexity and risk in their implementations, especially in very small devices. We also have dictionaries, which again is a fairly common form. Foo equals whatever, bar equals whatever, and they can be parameterized as well. And finally, inner lists in the dictionary values as well. And that's the basic data model we're working with. And so we consulted with a lot of different people who wanted to define new headers and find the set of primitives that worked for them. This is what we came up with. It took a fair amount of iteration, but we're pretty comfortable that this is going to hit the 80% mark. It may not be that every header in the world is going to fit into this, but we think enough are going to fit into it that it's going to improve things. And so for each of those types, we define very carefully an algorithm for how to parse it and how to serialize it, step by step in pseudocode. And we have multiple implementations to make sure that it actually works. So for example, these are a bunch of examples of what these things might look like. They look very much like existing HTTP headers in a lot of cases, which is nice. They're familiar. There's also another benefit to that we'll get into a little while. So the syntax is defined in terms of rich, well-understood types. Error handling, importantly for everyone, is defined in great detail. It's very clear about what to do when something doesn't fit the syntax. Usually explodes up. We have common libraries for parsing and serialization, and importantly, a shared test corpus to make sure that they all work the same way. I think right now we have around 1,500 tests. And we can then, because we're all reusing the same code, we can concentrate efforts on performance and security to make sure that they're the best for the headers that choose to adopt this. Currently, we've got implementations in Python, which was mine, Ruby, JavaScript, which I think the JavaScript implementation is not yet up to date with the latest changes. It's being implemented right now in Chrome, and C++, of course. We've got an Erlang implementation and a test corpus. And so the anticipation is once the spec settles down, we'll see a lot more implementations. But we have enough right now that we're pretty comfortable in interoperability, that we know that we've specified it well enough that it's written down well. We have a bunch of headers that have already adopted it, which is good. These are some of the folks we've talked to about making sure that it meets their use cases. And so that's kind of where we are now. We're pretty comfortable that this is going to improve the world in terms of making it easier to define new headers, having shared parsing libraries, better interoperability, better security, better performance. But having these data types defined actually gives us some new opportunities that are really interesting. I want to talk about that just a little bit. So first of all, backporting. Remember I said that they look a lot like existing HTTP headers. Indeed, if you take a list of existing HTTP headers and you map them to these data types, there are a lot of existing headers that fit really well. And so that gives you the ability to not only define new headers using as structured headers, but backward into old headers, so that you can use a structured header parser for an existing header in a lot of cases. Not every case, but a lot of cases. You can also map existing headers to structured headers. So for example, cookies don't fit into the structured header syntax, but if you understand the cookie data model, you can transform that into another structured header pretty easily. Secondly, is a little more interesting. Because we have a well-defined data model for these things, we can define a different serialization other than textual HTTP headers. We can define a binary serialization of these things. And so, there's a lot of complexity here that I won't go into great depth in, but if you, on HTTP2 or eventually in HTTP3, you negotiate the use of an alternate serialization, you can serialize these data types as binary on the wire and save yourself some bytes on the wire in some cases. So for example, binary data, if you've got binary data in your cookies or whatever, it won't be inflated with base 64 or whatever you choose to use, it'll just be binary on the wire. That's a win. If you have a date, for example, if you can serialize that as an integer, from the Unix epoch, that's a lot more efficient on the wire than a textual date, as we all do today. More importantly, it's a lot easier and more efficient to parse and serialize this binary format than it would be a textual format. And so in systems, especially, for example, a content delivery network, where the message is going through multiple hops, if you have a binary serialization, you're not deserializing and reserializing the whole thing again and again and again. It just goes through its binary data, which is much easier to handle. Yeah, so you still need a fallback. If somebody sends a header that doesn't fit into the structured header, you need to be able to fall back to just a string. And so that's part of the proposal that we have. And it gives you a lot of flexibility in choosing when and where to parse. The end game here is if we've been having discussions with the folks who do fetch. Who's familiar with fetch? So the HTTP API in browsers. If they expose these types in fetch natively, that means that you can have the data type never really become textual on the wire. It's binary end-to-end throughout all the different systems that it traverses, which is a lot more efficient. Finally, and probably most experimentally, once you have these data types defined, you can also fool around with doing structured compression. So if you remember in HTTP2, we introduced HPAC for compression. And HPAC works by taking an entire header field value and remembering that, if you choose to remember it. And then if the next message on the wire comes along and has that same whole header value in it, you get to say, oh, just reference to that one, and use one byte to reference it, rather than putting the whole thing on the wire again. And when we did HTTP2, we did some experimentation that showed that it helped quite a bit with performance. The original Speedy proposal was using gzip on the wire, if folks remember that. And this is the testing we did. I think this is the headers in a couple of interactions on Amazon. So it's 350 requests on the x-axis, and the y-axis is the compressed size of each header. And you can see the HTTP1, the blue line, it's, they're fairly big, and up the front, they probably got some big cookies on them, so they're like 1,400 bytes per request, which is horrible. But when you gzip the whole thing, the orange line, you get really good compression on that, because you're reusing that compression context. Unfortunately, we couldn't use gzip in HTTP2 because there were security issues with that, if you're familiar with crime, and so we had to come up with something else. And that was HPAC, and that's the green line here. And it's pretty good, because there's a lot of repeated, headers in HTTP, especially in requests. And like I said, HPAC works by taking the whole header value and remembering that, and then reusing it down the road. But we did that partially because we didn't have any visibility into the structure of that header. It's just an opaque blob. But once we have types for the different components of the header, once we have structured headers, we can do something where we remember little components of the header and say, okay, each value is a separate, effectively, cache entry that we can hit later on in the connection. So I did some prototyping on this. The red line here is that approach, using structured headers. Once you can parse all these headers, remember we've backported a bunch of existing headers into structured headers. You see it's about the same compression as HTTP2 and speed, HPAC and speedy. And the reason for that is, if you think about it, in HTTP2, if I've got let's say a really complex header, like cache control with a bunch of arguments, and it goes in the wire once, and then it goes in the wire again, I reference it with 1 byte. Great, really efficient. If I'm referencing each individual data structure that makes up that header value, let's say there are 5 arguments and each one's a key value pair, that's 10 different things I have to reference. That's 10 bytes. And so for a browser to server connection, it may not make a lot of sense. But if you've got a load balancer or a reverse proxy or a CDN, it might make a lot of sense because you're multiplexing a lot of different clients onto one connection if you're using H2 in the back end. And in that case, being able to remember more atomic data gives you a much better hit rate. And so it could make compression a lot more efficient in some cases. So, summing up, yeah, big win is easier, more complete header specification. We get the common implementations, the parsers and the serializers, and better focus for the performance and security engineering. There are some interesting opportunities as well. So it's still a work in progress, but the core of the structured headers bit is almost complete. There are some challenges into this. Like I said, we're aiming for the 80% case. We're not trying to fit every header in the world into this thing, but so far it's pretty promising that we're hitting the right mark for that. Getting the full benefits does require a lot of support in browsers and other places, but the interest we've been seeing is really good. And like I said, the compression benefits, the more forward-looking stuff is still very improving. So all of this, if you're interested, if you go into the first link there, the HTTP extensions repo, structured headers is one of the many different HTTP specifications we're working on right now. I also wanted to mention that the HTTP core specifications themselves are being revised. So if you're interested in that, that's the second link. The test suite that I mentioned is the third link. And the binary structured headers, that fourth link, is the more forward-looking experimental stuff. And finally, if you're interested in those cache tests that I mentioned, that last link is where you can find a lot of really detailed tests for proxy and browser caches. That's all I've got. The only other thing that I'll mention is that if you actually found both of the talks tonight interesting, there is another event that we hold. We're just planning the next one for this year, and it's going to be not too far from here. And it's called the HTTP Workshop. And it's 2 or 3 days of all the HTTP implementers from all the different implementations around the world getting together and talking about the details of the protocol and where it's going. Everybody seems to think it's a pretty good event to go to if you're interested in this stuff. So we're trying to broaden that community. So if you're interested, keep your ears open. There'll be an announcement soon. The website is httpwork.shop, which we had a lot of fun with that. But we'd love to see some new faces there. So, yeah. Any questions?
Thank you, Mark.